Okay, let's begin. Good afternoon to those of you across the country, and good morning to those of you on the West Coast. My name is Max Martina. I'm the president of Griswold Water Systems, and I'm happy to welcome you today to this brief webinar on water savings. We'll spend about 30 minutes or so in a conversation covering three key issues. Bring that screen up here so you can see that. I will be recording this session, and we'll make a playback available to those of you who would like to see it again. In today's conversation, we're going to cover essentially three topics. We're going to give you an overview of the water conditions in the country and the role of water savings for building and HVAC systems. We're also going to cover technology and the application of technology. We will not cover our core product principles of operation, however, and as such, we simply don't have the time to get into those details. Many of you that are reps know that. For those of you that are customers, we have a separate presentation that discusses the principles of operation for our primary non-chemical water treatment system. So we'll cover that. You can cover that on a separate presentation. Let's talk first about water supply in this country. This is a graph that you've seen before, perhaps. It comes from the National Resource Defense Council, and it estimates the sustainability of all freshwater resources in the country and where those resources will stand in 2050, so from about 34 years from now. You may know that in 2012, this country was hit with a significant drought. The costs exceeded $35 billion in insurance claims, and that's not just for industry, but that's primarily for agriculture. It takes a toll on the U.S., especially in the Midwest and parts of the Southwest, where you can see we have natural desert topography. Humanity has done a great job in bringing irrigation and water to that part of the world, and so we have a surging population in some of those regions. Take a look at this data from NASA's GRACE satellite mission, which uses satellite-based radar to analyze the freshwater resources in all of Earth's major 7 natural aquifers. Now, these aquifers are crucial because this is where the bulk of freshwater supplies come from for the potable water needs of humanity. These aquifers are millions of years in the forming, and you can see that over the last decade or so, the trend downward towards the consumption of the water within these aquifers is negative. I'll have you note two specific lines. The blue line is the Southern Plains line, as well as the Central Valley of California, which is the yellow. And you can see that the trend is downward, which is to say we're tapping groundwater resources faster than we are replenishing them. And again, these aquifers take millions of years, certainly thousands of years to replenish naturally. So as we use these resources, we are depleting our available supply. This slide is to showcase the fact that pollution also impacts supply. You can see here a map of watersheds containing impaired water bodies. This is from the U.S. Geological Survey. An impaired water body, by the definition of the USGS, is any water body that does not meet the state's water quality standards, either in chemical analysis or physical analysis or biological analysis. So you can see the darkest areas on this map are counties that have water supplies that are considered impaired in excess of 25% of that county's available water supplies. So you can see here that the major contaminated water areas are those that have heavy agricultural impacts as well as industrial impacts over the years. So obviously pollution will impact supply. In many cases, it's already impacting supply. We talk about supply, we have to also talk about demand. Here's some simple macro data from the UN Environmental Program that shows global water use and global population growth. And what's key here, of course, isn't just the fact that these two lines are both going vertical, but it's the increasing distance between water withdrawals and global population. So while U.S. demand is relatively static over the last 100 years or so, you can see that this data is skewed significantly by developing regions. In other words, demand is outpacing population growth. And as our aging infrastructure continues to age, I should say, then the water wasted in certainly the developed world is also increasing as well. The point of this slide is just simply to say that we have dwindling supplies and we have increasing water demands. When that happens, the natural laws of economics are at play. Tightened supply and demand increases equal price increases. This is data from 2012 reported in the newspaper USA Today. And you can see that in every major metropolitan area, there are price increases for water in the United States. Water rates are up 6% in 2013, the latest data that I could find, but they have doubled the consumer price index every year since 1996. So many of you who look at your wastewater bills will know this, that especially the cost of wastewater is going up, but this really is about the potable water purchase costs for both residential and commercial applications. This is the trend. This is going to continue. There's no question about that. As people become more aware of the scarcity of water and the increasing consumption of water, we need to be cautious about our costs related to water. There are many drivers for a new paradigm for water efficiency. Dawning global awareness of water scarcity, as I've just discussed. Obviously, the impacts of pollution are part of that. You also have LEED and environmental drivers. LEED began a very popular push in the marketplace in the early 2000s. And I think the organization of USGBC has done a great job spreading the word of our need to improve building management and building efficiency. I don't know if LEED is still a gold star program and it's being pursued widely, although engineers tell me that in fact the standards are being pursued widely, but the marketing credential that it provides may not be as relevant. Lastly, the high operating cost of cooling systems is something that building operators and managers, I think, are beginning to wake up to. Typically, as you all know, cooling towers are out of sight, out of mind. Most people are focused on the cost of water in potable uses in the building: dishwashers, laundry, water and sinks, toilets, flushing toilets. But the reality is that water in commercial and industrial buildings is often consumed in large quantity by the cooling systems that occupy them. This is Bernard's first cooling tower, produced in 1903. It was a wooden cooling tower, a fanless cooling tower. And while things have changed substantially in the cooling world, the basic design of a cooling tower has not. The idea is that by evaporating water, you can cool the water and remove heat and then transfer that across to the building. But we know that cooling towers use significant inputs, and those inputs include electricity, water, and certainly chemical additions have been required for decades. What are the economics of water consumption in buildings? Many of you have heard this if you've been a rep of ours. If you're a customer, this might surprise you. The total cost of operating a cooling system, if you factor in the purchase of a cooling tower, the chemical costs that are used to treat that water on an ongoing monthly basis for the life of the equipment, the water costs and the energy costs are all inputs that are over time very expensive. Many people look at the bills and they think, well, this cost is largely attributed to certainly the chemicals. The reality is much different. You can see here that on average, water treatment, it costs less than 2% of the tower operating cost. So the big chunk of operating a tower in terms of cost is both water and sewer, 25% there in the blue section, and energy cost, about 71%. So we have a significant opportunity in front of us to improve the efficiency of our operating systems to cut overall cost. And that should be our focus. That should be I would argue that every building manager and operator should make system efficiency a significant focus if they want to drive down costs. Said another way, focusing on the cost, the operating cost of chemical inputs is penny wise and pound foolish. Consider the non-energy cooling tower inputs. We're going to leave energy aside, even though that's a significant chunk of costs associated with a tower. For an example tower, this square represents a cooling tower operating at 75% load year-round, akin perhaps to a data center. 1,000 tons of cooling at 3 cycles of concentration. A tower of this size will consume almost 18 million gallons of makeup water per year. That's a lot. That's approximately 26 Olympic-sized swimming pools every single year. Because evaporation is constant, 12.5 million gallons approximately will be evaporated into the atmosphere, roughly 70% of the total makeup. And the chemical inputs are also significant, anywhere from, and this is just a range, but this is an average, about 4,000 pounds of chlorine, 1,000 pounds of corrosion inhibitor, and up to 70 gallons or more of biocide. That's the really nasty stuff that is toxic to life. Output includes 5 million gallons of blowdown to the sewer. So you can see cooling towers are resource intensive. The question comes, what can we do really to improve the efficiency of this system? These cooling towers have been around for 100 years. How can we improve its operation? And the best way to do that is to improve cycles of concentration. We'll talk about cycles of concentration in a minute here, but it's essentially a measure of the total number of dissolved solids in a tower, which is to say we're going to use less makeup water. We're going to concentrate the minerals more directly in the bulk water supply, and we're going to evaporate less or fewer chemicals. Less water. A tower like this, same tower, but running now 5 cycles of concentration, with the assumption that no chemical inputs are required, will consume 3 million fewer gallons of water per year, or 14.7 million gallons of makeup water. Evaporation is constant, again, so you have 12.5 million gallons evaporated. And you're going to discharge roughly 2 million gallons, which is equivalent to saving approximately 3 million gallons of water. Without chemical inputs, that's just slightly harder water. And that water can be used on site, and it can be, or at least dumped over to storm drain without incurring any sewer costs. This equates to approximately more than 25% of water conserved in the system. From a financial standpoint, the simple savings here is about 14% in terms of total costs for the system. That equates to, in 10 years, about $700,000 in savings. This is without reusing that blowdown. So you can imagine that when you reuse the blowdown, the cost savings are enhanced significantly. Of course, the bulk of this, from a water standpoint, a water and sewer standpoint, is there between the difference. You can see my cursor on the screen between these two lines of the water and sewer graph. By operating the system more cleanly, you will eliminate inefficiencies attributed to scale buildup and biological growth in the system, and that will help support efficiency in the tower. So there are a lot of opportunities here for improving efficiency in cooling tower operation. Let's just talk a little bit about what cycles of concentration are for those of you that don't know. It's simply a term used to indicate the number of times dissolved solids in a particular volume of water are concentrated. So when you run a tower at higher cycles of concentration, you use less blowdown water, and there's less total water use. If you run lower cycles of concentration, which is to say simply makeup water pass through the tower one time before you throw it down the drain, you're going to use significantly more water. This is a chart that explains what that might look like. We all know that in water, unless it's distilled, of course, there are dissolved minerals. And as you concentrate those minerals from 1 cycle to 2 cycle, you can see that the portion or the quantity of those minerals doubles. And that proceeds forward until you get to any number of cycles, upwards of 8, 10 or so, which is a theoretical maximum for efficiency in a cooling tower. You can see that this is the volume of water used to support the same cooling load. So you have essentially approximately 75% savings when you run a cooling tower at 8 cycles versus 1. Here's the graph that indicates blowdown water savings, and the same is for makeup as well. The savings between 1 and 2 cycles is huge. It's tremendous. Over 50%, about 50% of your water is saved. When you move from 2 to 3, the savings diminishes, but it's still significant, 25% of water saved. And I mentioned a theoretical maximum of 9, 10, 11, or 12 cycles around there when you have diminishing returns in terms of water savings. But in areas of the country where water is particularly hard, like in Southern California, for example, most cooling towers are running between 2 and 3 cycles. So anything that can be done to improve cycles of concentration will result in significant water savings. And of course, if you have a significant volume of water or a lot of cooling, even moving from 9 to 10 will yield significant savings when the volumes are large enough. A component that's necessary in all cooling systems, as you may know, is a blowdown system, a functional blowdown system, which includes a conductivity controller. And in this case, it includes a toroidal probe, which passes electricity through the water. And based on the conductivity, the amount of electricity returned, it can calculate the amount of dissolved solids in the water. When those dissolved solids reach a certain threshold due to evaporation in the cooling tower, then the conductivity controller signals the motorized ball valve to open, and bulk water is blown down the drain, forcing the cooling tower to add new makeup water, which is coming in at a much softer level. Its makeup has less dissolved solids than the bulk water supply after evaporation. So this is required in all cooling systems, and oftentimes we will see limitations of the water treatment related to these components, whether individuals are pursuing chemicals or non-chemical systems. Let's take a quick look at modern water treatment goals, and then we're going to get into a sidebar in technology. Modern water treatment goals are really about making tower operation more efficient, and this can be done significantly through improved water treatment. We're aiming to do essentially three things: provide effective heat transfer, into the process controlling mineral scale and biofilm. We aim to protect capital equipment, of course. Cooling towers are expensive. We want to maximize water efficiency. This is something that's rarely accomplished by chemicals. Of course, we want to manage solids for cleaner systems, and this is largely to reduce or mitigate the risk of Legionella and other biological contaminants, which of course is a health risk to humans. And we want to avoid contaminating air, water, or ground. This is also difficult with chemicals when you're inputting toxic biocides, which must be discharged to sewer. Well, water treatment problems, whether they're chemically related or non-chemically related, are usually attributed to one of these four things. In the case of chemicals, incorrect chemical dosing. And this happens oftentimes and can result in the premature life of the tower, especially with slug dose oxidizing biocides, which can create problems in a cooling tower basin, for example, and pitting. Poor operational practices on behalf of owners and operators, because the cooling towers are out of sight, out of mind. This happens many times. Ineffective solids management, which can lead to breakouts of Legionella and other biological growth within cooling systems. And inadequate monitoring or monitoring service of the tower. So not necessarily knowing what's going on with the system because no one's paying attention to it. Let's talk a little bit about the status quo of chemical treatment. And chemical treatment, of course, has been around almost as long as cooling towers. Chemicals have been the go-to approach for decades upon decades, and when properly applied can work very well. So this slide is not to demean chemicals. It's simply to show you the balancing act that using chemicals creates for a service partner. In this case, with a cooling tower using chemicals, toxic biocides are often added to kill the bacteria. And that's important because, of course, the risk of Legionella is real. And without biocides, water will breed life. And there's just no question about that. Biological results can be quickly ascertained with a simple dip slide test or other more complicated lab tests. And that's something that most operators are very sensitive to. The problem is that toxic biocides are usually oxidizing in nature, and they're very caustic for cooling towers. So in order to compensate, chemical service partners will add inhibitors to control corrosion. The trick is that many of these corrosion inhibitors are phosphate-based, and phosphates, as you may know, are fertilizers. And fertilizers, of course, will be used to create biological life or to support biological life. So you have this back and forth between killing bacteria and adding fertilizers that grow bacteria to protect against corrosion. Meanwhile, operators have to consider scale because if they cycle the tower too high, scale will form on surfaces and complicate operation, reducing energy efficiency and heat transfer. So scale inhibitors must be added to keep calcium in solution in most cases. This process is repeated ad infinitum for the life of the tower. Chemical inputs are continued and necessary every day, every month for the life of that tower, whether it's 5 years, 15 years, or 30 years. In addition, oftentimes biocides must be rotated because certain bugs become inoculated to the biocide that was originally added, and so now service partners are rotating biocides. This is like chasing a target, like the carrot in front of the rabbit, always running to catch up with the system as load changes or as demands change within the system. On top of this, keeping cycles of concentration low to avoid scale is in the best interest of the service partner, because if you have to cycle the water higher, the risk of scale is greater, and that's a problem for the service partner if the scale forms. So many service partners will do what's called feed and bleed, which is to say keep cooling systems running at artificially low cycles of concentration. And by doing so, they eliminate the risk of scaling. They also waste more water and therefore can sell more chemicals, because more chemicals go in and therefore more chemicals go out in the drain. Again, reputable service partners will not do this, but those that own blending shops are predisposed to this simply because they have an incentive here to sell more chemicals. That's just the name of the game. So here's the industry model that folks are very familiar with: monthly human service partner visits. The inputs in this case, of course, are continuous chemical inputs for the life of the system, resulting in an equilibrium that is rarely achieved. As temperatures change, as load changes, as demand changes for the cooling system, or even water chemistry changes, it's very difficult to chase after all of those effective results. The dose, either chemical guys will feed and bleed or they will slug dose towers. The concerns with this are many, including injection pump failures, premature chemical depletion, overdose of chemicals, of oxidizing biocides in particular, which can damage surface metals. I have seen dozens, perhaps hundreds of towers that have been destroyed due to chemical inputs. And let's talk a little bit about HVAC system fault frequency, because what I'm talking about here now is not necessarily the fault of the service partner. It is simply the fact that cooling systems are complicated systems. There are multiple moving parts, such as blowdown valves, makeup valves, pressure, temperature sensors, many moving things. There's fill, there's variable speed drives, a whole bunch of things within a cooling system. Inevitably, as multiple chemical service partners have told me, there will be, in a given year, 25% of all of the service partners' jobs experiencing some kind of hiccup. Again, this is not necessarily due to the chemical injection failure, but it's more likely due to a broken makeup valve, a broken or a stuck discharge valve, a blowdown valve, for example. And these things happen all the time. The challenge is, under chemical treatment, that if a service partner shows up on January 1st and the makeup or blowdown valve sticks either open or closed on the 2nd, then that cooling tower is effectively without effective or under a state of crisis for the next 29 days until the service partner returns. What this means is their mistakes are compounded, the mistakes that have occurred as a result of system operation mistakes, and therefore you end up getting this accretion in problems within the system. So you have premature system life, and you end up ultimately wasting significant amounts of water. Let's look at the results from that. There's a significant lag time between human service partner visits and the system upsets that occur on average 3 times a year for a given cooling tower are between 1 and 30 days, which is an average lag time of 15 days. Over a 15-year life of the tower, you're talking about 675 days without effective service over the 15-year life of the tower. That's almost 2 years of a 15-year tower lifespan to effectively have the tower out of calibration. Again, this is not necessarily the fault of the chemical service provider, although sometimes mistakes happen there. It's really the fault of the operating conditions of the cooling tower, something going wrong downstream of the system. There's no record keeping on water consumption and discharge habits because monitoring that becomes expensive. Chemical service partners are often not, they're incentivized to blow down more water to support chemical sales. So this fights in the face of what the goals of the owner-operator are in terms of water savings. Compounded problems can quickly degrade system life. As I mentioned, the example of a problem occurring downstream on January 1 and the tower sitting uncontrolled for 29 days until the service partner returns to visit. And then huge unnecessary increases in water and energy costs with little visibility from the customer create a disconnect between accounts payable and a system operator. Lastly, because there's little accountability on behalf of the service partner, he or she does not technically control mechanical function of the system. So if you have a blowdown system error, it's your problem. Can chemical dosing incorporate monitoring technology? So this has been something that chemical service partners have looked at for many years. And the answer is yes, but it's expensive. Here's a simple example here of a system that's used on cruise ships and cooling towers across the country. They require multiple tank level meters, accessibility to dosing pump status, communications and transmission to surface partners, compatibility to conductivity controller. All of this is to say that costs for such remote monitoring systems are expensive because you're dealing with liquid chemicals and measuring their inputs. Most operators are unwilling to provide or pay for the cost associated with that. I'm going to share now with you our approach to the solution here, which I believe is transforming the industry because we're taking a new approach to saving water and treating the system in a holistic fashion. Many of you have heard of this. It's called IntegraClean 2.0. We view this as the best solution. Of course, I'm biased, but I can explain my reasoning, I think, directly here. We have three primary goals, and those include eliminating toxic chemicals, mitigating the risk of biological outbreaks, and enhancing water savings and system efficiency. This system, a package system for easy install, includes several key components. The first is the wave, which is the non-chemical electrodynamic frequency water treatment system that controls scale, biological growth, and corrosion, controls conditions within the tower to promote low corrosion. It includes a high-efficiency clean sweep basin system, which requires half as much energy as traditional basin sweeping systems. A centrifugal separator used to capture sediment from the tower and promote very low biological counts within the system. And this is all done in a package system which incorporates remote monitoring. So I'd like to switch gears just briefly here before we conclude and talk a little bit about what that remote monitoring does when it's coupled with this type of equipment. Insulet remote monitoring is integrated into every wave that we sell. Every wave control panel automatically comes with it. It supports accountability and transparency of the system operation. It is essentially a wireless communication tool that collects data and transmits that data to ourselves and our service partners. It sits inside a NEMA 4 control panel, water resistant. We can get NEMA 4X as well if required. It's pre-wired to reduce installation costs, as is the entire system. And it measures or monitors three key parameters. The first is that the wave is doing its job, which is to say that effective water treatment is taking place, which is to say, another way of ensuring that scale is under control, corrosion is in check, and biological growth is effectively being treated. Also, the second parameter is conductivity of the recirculating condenser water. This allows us to infer if there is a system hiccup. So, for example, if a blowdown valve sticks open, that means water is going to drain from the tower, and new makeup water will come in to meet the level meter. When that happens, conductivity will drop below our set point, and we will know that there is a leak in the system, a valve stuck open, or perhaps there's been heavy rains. Same is true if the valve sticks closed. Conductivity will spike, and to avoid scaling a tower, we will know that very, very quickly. The third thing we're monitoring is system flow. And of course, system flow tells us that there's recirculation in the system, something that's also crucial when using chemical inputs. With these three key parameters, we can essentially eliminate 98% of system upsets that have nothing to do with the water treatment specifically. The other key part of this is that this system is scalable to measure water volume inflows and outflows. And this is something we're just pioneering now, and I'm happy to discuss this with you more offline. I'll share some exciting results that we've had here in just a second. This supports low-cost, seamless monitoring of key parameters to ensure optimum system treatment. It's not expensive. It's integrated into wave water treatment. It's non-invasive, so there's no firewalls required. It's a simple 3G, 4G cellular network. It's accurate, virtually instant real-time data collection and transmission, as long as our conductivity controller is properly calibrated, which is something that's checked by the service partner. And it supports the immediate dispatch of human service partners as required. So what this means ultimately is that service lag time is diminished or eliminated. And ultimately, real-time monitoring of additional system inputs, including water's inflows and outflows, will allow customers to save significant water and therefore significant dollars. And I'll show you some data here in just a second. So here's the new paradigm that I'm proposing here and that we're having an impact on in the marketplace. We're now going to incorporate our non-chemical treatment system, and in that process, harness wireless technology to support monthly human service partner visits supplemented in real time as required. So with a package system now, what happens? We have zero inputs, electricity aside. Of course, that's required in chemical feed stations as well. The result is that you have treatment equilibrium regularly achieved. The system is much more resistant to occasional downstream system upsets. Dosage, there's continuous treatment as long as there's recirculation. So there are no chemicals required in the process, which means that blowdown can be reused on site. No concerns there. But let's consider that there are system upsets in the same as with chemical inputs at the rate specified by most chemical service partners, which is to say 25% of their jobs in a given service partner's visit will experience a system upset. Equated to a single job, that means each cooling tower will have 3 hiccups per year. And those asterisks, those problems can be read about in the asterisk down there, which include broken blowdown valves, broken stuck makeup valves, valves oriented in incorrect positions due to installation error, etc., etc. When these system upsets occur, because of remote monitoring, they can be caught very quickly. Here's the upshot of that. First of all, lag time between human service partner visits is now 0 to 2 days. On average, let's say 1 day. So if you have 3 system upsets on your tower per year, which is inevitable, according to the chemical service partner experts, that means over the 15-year life of the tower, that's 45 days without effective service life. That's a much different result than 675 days under chemical treatment. That's a 93% reduction in unserviced hours. You now can support detailed record keeping on water consumption and discharge habits, which both educates owners and operators and accounts payable. This means that we have the incentive to help save water. We're not discharging chemicals and therefore selling chemicals. We are not compounding problems, which is to say the accretion of scale does not occur. System life is preserved and water conservation is maximized. This results in huge cost reductions in water and energy, and the accountability of the service partner and the owner-operator is enhanced for mutually beneficial goals of efficient, well-run towers. So you can see here that the status quo of chemical service has been rendering the quality of the local service partner, which is to say that many people are satisfied with their chemical service insofar as their local chemical service partner is competent and capable. In cases where they're not, the name of the game is fire and replace. So I know many customers who've been through 5, 6 chemical service partners in a 5-year span looking for a partner that really understands what they're doing. Because the opportunity for efficiency gains are so great in cooling towers, the resource-intensive nature of towers has prompted a history of searching for new solutions. Many technologies have been debunked or stymied as by a result of lack of science or human service over the years. And increasingly, however, with effective solutions, people are using remote monitoring to support this accountability. That's how the industry is going. You may have heard of the Internet of Things, in which communications are increasingly required between static pieces of equipment. This is how building management systems are proceeding, and this is how cooling systems are proceeding. It's really the state of the future, which is to say that communications will increase. And I believe this package does that quite effectively while offering a comprehensive solution for solids management, effective water treatment, and remote monitoring. So I'm really convinced that we can do this so well that we offer a performance guarantee. This performance guarantee allows the customer to obtain 100% of their money back, and we will agree to meet industry standards. This includes water savings. I'm not aware of any other company that will promise water savings, but we will do that. I always include a few cases of some of our longstanding customers that have praised the heavens about us regarding our success. One is UC Davis. Tim Essert was the facility director there, and that system's been in place for many years. They're very happy with that, and it's eliminated the scaling of their heat exchanger. Another job for us that's very dramatic results on biological shows a bakery in Jacksonville, Florida, which was actually venting their kitchen exhaust fan, which included yeast, of course, into their cooling tower. The biological count for this system was over 1 million, and after approximately 4 weeks, you could see bacteria counts were less than 5,000 colony forming units per milliliter. The system is very effective. Now, what does this mean for water savings? I'm going to show you some real data here. This is what InstAlert, the remote monitoring portion of this, allows us to do. You can see the captured data from a job in Southern California, upon which we have a complete IntegraClean system which fuses remote monitoring. And in this process, we are monitoring inflows and outflows of water in addition to system performance, recirculation, and conductivity. So in any given hour, we can tell with virtual certainty what the tower is currently doing. What that means is we can track conductivity in the tower. And you can see here that the conductivity started at 1800 at our suggested set point. We had a spike and we had drops. In a couple cases, we had the remote monitoring offline, so we couldn't collect the data. This has allowed our service partner to be in touch with the job operator and understand very quickly and clearly what's happening to the cooling tower. We understand that a lot of these spikes and dips have something to do with system operation, in some cases rain, which actually will dilute the conductivity of the cooling tower. This matches up with weather reports and specifically the data on site with the customer. Cycles of concentration, which are cumulative here, is also something we can determine as a result of measuring inflows and outflows. You can see the typical cooling tower operating cycles of concentration will occur between 2 and 3 cycles in this part of Southern California with very hard water. And you can see that as the cooling season heated up or increased over time and temperatures rose, we were able to further concentrate the minerals within the tower. So what this means ultimately is that we can track down to the gallon the amount of water consumed and discharged to the system. A significant advancement in the industry for water savings. Let's talk briefly about water savings and payback on the financial side before we wrap this up and take a few questions here. This input data shows a cooling tower that was demonstrated earlier in our example of 1,000 tons running at 75% load year-round, say for a data center. Chemicals operating at 3 cycles of concentration can be converted to, with wave, approximately 5 cycles of concentration, which is to say we can concentrate the minerals greater. Water cost in this part of the world is approximately $3.50 per 1,000 gallons, and the discharge costs, which are often double that of the purchase costs, in this case are $5 per 1,000 gallons. So you can see discharge is very expensive in these regions. We compare the average service cost of a system here for chemicals, and you can see quite quickly that the payback is significant. Down here in the green, annual water savings show approximately 3 million gallons of annual water savings, or 16.7% in this case, simply by increasing 2 cycles of concentration. In this case, you can see that the chemical water treatment program cost was about 3.5%, so a little higher than my earlier figures. But wave water treatment cost is more like 1.2%. That shouldn't really concern the owner-operator. What should concern the owner-operator is the operating cost, because what we're talking about are annual savings of $45,000. That leads to a less than 1 year payback, of course, but those annual savings are certainly significant when factored over the life of the equipment. One final case here before we end this, and that is reuse that blowdown water. Why? Because it's chemical-free. It's not saturated with toxic biocides. And in every municipality that we've researched, the authorities will allow that discharge, that blowdown, to go over the side of the building, which means that the customer no longer has to pay the sewer discharge fees. And when that happens, payback improves even greater. You can see that the water savings is 2.9 million gallons, the same as before. If we were to reuse that on site, the water savings would be much higher because we would discharge other potable water uses from the consumption of that from that blowdown, which could be reused on site. In this case, the payback improves to less than a year by about 3 months, and total savings annually are closer to $60,000. I'm going to stop there and thank you for all of your time. I'd like to take some questions if we have any. So please use the chat screen on your bar, or excuse me, the question screen on your bar to ask those questions. I'd like to ask Carol, our marketing director, to chime back in and funnel those questions to me if you could. Those questions I'm happy to answer those offline as well, but if you have time and you want to raise your hand now, we can discuss those publicly. For those of you that can't stick around, I thank you for attending. I will make a recorded version of this presentation available to you, and we'll stay on the line here for a few more minutes to look for questions. I don't see anyone raising their hand. We'll give it a couple more minutes here so that you can use your control panel, go to webinar control panel.
Hi, Max. This is Kat.
Hi, Kat.
We have a question about how are we able to reuse the cooling tower blowdown with Wave?
Sure. Good question. So cooling tower blowdown, of course, is it's just like regular makeup water, but it's been cycled a little bit higher, which is to say it's slightly more saturated with minerals. That water is quite useful and quite benign. So the question becomes, how can you capture that? Really, I think is where you're going with this. Griswold Water Systems does not assemble systems for the capture and reuse of that, but it does require a series of cisterns and basins for distribution on site. Many people will take that blowdown, and if they do not want to discharge it over the storm drain, for example, and avoid paying sewer discharge fees, they will capture it in cisterns and mix that with other potable makeup water, for example, for use on site. Many people will reuse that for irrigation. Some people will funnel that into the building system for toilets, for example, gray water toilets, and reuse that way. And in most cases, it does need to be treated for biologicals, but that could be done with wave treatment as well. It would not be used for a potable application, but certainly for toilets would be appropriate.
Okay, thank you very much. Um, Reba Schreiber wants to know how the electronic treatment works. Do you want to give us a thumbnail of how the Wave works?
Sure, Rita. Good question. I did mention at the beginning that that was largely beyond the scope of this, but I will give you a snapshot. The technology has been around for more than 8 years. It has well-published papers on the efficacy of the technology, certainly as a biological control agent. And the thumb sketch for this is really 3 areas that we're working with here: scale, biological growth, and corrosion. For scale, it's a pretty elegant solution. As most chemical service partners will do, they wish to keep minerals in suspension, which is to say dissolved in the water. We take the opposite approach. We want to precipitate those minerals out. And what we're using are suspended particles of dust, dirt, debris, and sand in the water to do that. The wave, through its electrodynamic signal generation, will simply strip the surface charge off of those suspended particles, allowing those suspended particles to be surface nucleated sites for scale formation. So, which is to say that as the water is further concentrated, then eventually the driving force exists to pull those minerals out of solution, which is to say form scale, and the scale essentially forms on those suspended particles. That's for scale control. For biological control, the wave emits a powerful electric frequency which pierces the cell wall of the bacteria and also encapsulates the bacteria in that powder. And we see biological counts oftentimes at the levels of drinking water standards, less than 500 colony forming units per milliliter per year. And as far as corrosion controls, by precipitating out calcium carbonate in the bulk water supply, preventing it from sticking to other system surfaces, heat transfer surfaces, that calcium carbonate is a benign cathodic corrosion inhibitor. And that means simply that the water is less caustic or less corrosive, I should say, and natural corrosion occurs as a result of that calcium being present. So that's the short story. We have visuals that can illustrate that, and we have a separate presentation that covers that as well. I believe you can find that on our website, and we can also talk further if you have more detailed questions.
Okay, great. Thank you. Thank you very much. We had a question also about how Wave destroys microbes, and I think that you gave a good quick sketch of how that is too. I do just want to reiterate that we're very open to talking about our technology, and since it's not the scope of this webinar, we're welcome to do it. We're happy to do it offline. Um, we have a question about, does it matter the type of cooling tower, or does our system work better with certain types of cooling towers?
Yeah, good question. The focus for this equipment is evaporative cooling. So whether you're talking about a standard cooling tower or an evaporative condenser, um, it really doesn't matter. The key for this technology is that you have circulation through the wave system itself, that you can see multiple passes through that system. Our wave technology, the signal emission is so strong, in fact, that we will actually use this on a side stream basis. So we require a minimum of 20% side stream on a recirculating application, which is to say that if a cooling tower or evaporative condenser, for example, is circulating 1,000 GPMs per minute, the wave has to see approximately one quarter of that, 200 to 250 gallons on a recirculating basis. So the short answer is no, it doesn't matter as long as we're talking about evaporative heat transfer and recirculating applications.
Okay. Um, on existing systems, how long will a cooling tower system require shutdown during the retrofit?
Good question, very good question. We have a couple different ways that we can install the equipment. The approach that I'm most in favor of is the side stream cooling tower, which is, I'll bring up a picture here if I can.
Okay.
One second.
We're getting another question, a little more depth on our biological control.
Sure. Kat, hey, Carol, let me just finish this question. I wanted to show the picture. That's okay. My preferred approach to our installation is literally doing a side stream application, because that allows us to essentially leave the cooling tower running for the installation process. The exception may be the installation of the sweeper system that you can see in the basin here, for example. But if you have a fairly open basin where the fill does not come down all the way to the floor, for example, then it can be literally put in there. For existing cooling towers, you can actually go over the sidewall of the basin. We do not need to make perforations in the basin sidewall, and so installation is very quick and very straightforward. If the customer wants to go full flow with the wave component, and that might be required in some unusual applications, or if you're wishing to treat a common recirculating header, for example, then of course you'd have to splice into that recirculating header, and the shutdown time corresponds to whatever that would take to slice and weld flanges in for a 4-foot section of pipe. But the short answer is that for side stream applications, there is often no shutdown required. Go ahead, Carol. What was the second question on biological?
Yes. There's a question that's, does this system completely eliminate the need to add biocide to the cooling tower water? And what does it measure to ensure that the bacteria levels are eliminated?
Great question. Great question. As you know, bacteria is measured in a cooling tower through multiple types of tests. One of the most common is a HPC, heterotrophic plate count, which is to say they take a sample of the water, incubate it in a lab, and then count the number of colony-forming units under a microscope. And chemical service partners will do that oftentimes once every 6 months, sometimes a bit more often. Sometimes they'll use dip slides, which is a simplified version of that test, on a monthly basis, and they're highly subjective, because you're counting little circles of cultures on an agar dip slide, for example. The best way to discern whether there's biofilm is in a system, especially in a cooling tower basin where you can access the system, is literally by feel. So if you feel in your cooling tower basin and it's like a slimy, slippery surface, that is biofilm. It's the same type of feeling that you would note if you felt the inside of a pet's water dish, for example. If you've ever had a dog and you felt the inside of a dish and it's slippery, that's biofilm. It's also like walking across a stream and there's a clear rock, but it's slippery on top. Well, that's biofilm. So the best way to tell is by touch. And oftentimes you can get into chemically treated towers and feel that biofilm there. And if it's in the cooling tower basin, then rest assured it's in the condenser tubes as well. In our case, the system is so effective at biological control that when we do heterotrophic independent lab certified tests, which often come back far lower than the CTI recommended standard of 10,000 colony forming units, and in numbers closer to say 500 or possibly 1,000, somewhere in that range, that corresponds to absolutely no sensation of biofilm in a cooling tower. So we know that if we have circulation within the cooling tower and that the wave is on and its set parameters are appropriate, then we know we're controlling biofilm to that degree. So no specific tests are required. However, our service partners, when they service the site, will do a field test, and they will also take a water sample test as well on every visit. And so essentially, there is no direct measure of biological within the system, but there's an indirect assurance that we have based on effective conductivity parameters and recirculation flow. I would say that the most important indicator of biological control is flow through the wave. So if we have recirculation, then we know we're effectively controlling biological growth. And we do monitor that.
Any other questions? I have one from Dave Terrell about locations of where we have various waves. And David, I'm going to answer you offline.
Good.
Okay, I think that's it.
One follow-up comment, Kat, and that was an independent analyst recently published a paper at CTI, Cooling Technology Institute in Dallas, actually two papers, one last year at the conference in, I think it was February, and a second follow-up paper this year in February 2016, both of which are specific to cooling tower performance under wave treatment. And there is a long section in there about biological control and the effectiveness of these systems for biological control. If any of you have heard of a poorly done study by ASHRAE that called into question the effectiveness of these types of systems on biological control, that study was subsequently discredited. We have statements and papers on that as well. And there have been since multiple studies that have published the opposite findings, in fact, that these systems are very effective for biological control, as long as there's circulation, which of course there should be in any appropriately treated cooling tower water, even with chemicals.
Okay.
Great. Any other questions? If not, I thank you all for your attendance and your attention. And your great
Hang on one second.
Sure.
I think we have. Can you describe the level to which this system has been proven, such as discuss the current install base? How many years has this technology been in service?
Sure, good question. Yes, predecessors of Wave, you may know some of their brand names, have been in the marketplace for about 9 years. Evapco, a cooling tower manufacturer, so believes in the technology that, in fact, they purchased one of our competitors to use this in the marketplace because non-chemical has been a strong desire of customers. In fact, this whole technology approach was driven by customers as recently as 10 years ago. But regardless, there are hundreds, I would say thousands of electrodynamic systems in the marketplace. Griswold has installed and sold over 1,000. IntegraClean here, as you can see it bundled together with our filtration package and clean sweep system, low head energy efficient clean sweep system. It's a fairly new development for us, but they used to be sold in components, and we've since packaged it. So hundreds of systems exist in the marketplace. More like dozens of systems more recently have been put in the marketplace and have been run successfully in terms of the comprehensive filtration package. But Griswold Water Systems started as a filter company. So we've had quite effective filtration systems in the marketplace for years. And it was important to the founder of this company to ensure that our reputation was upheld and strengthened by effective technology. So we have found that there is a tremendous synergy between non-chemical and our filtration products, coupled with remote monitoring for the reasons I explained before, simply because the delivery mechanism of the components supports remote monitoring, and it supports effective field performance. Carol has a list of dozens, if not hundreds, of installations that we've had in the marketplace. Many of them have been in the US, but we do have several international partners as well and accounts, so she can provide information about that. The short answer, circling back, is that Wave has been a proven technology for about a decade now, and we have multiple independent studies which will attest to that.
Okay. One last question, Max,
Sure.
from one I can see. What is the required flow rate through the Wave? And is the Wave supplied with the separator?
Let me take the second part of that first. Wave is not required with the separator, or vice versa. The separator is not required with the Wave. They do two different things, though, just to be clear. The separator and conjoined sweeper system are about solids management. And it's my opinion as a filter company president here that all cooling towers should have effective solids management, because solids management is part and parcel of mitigating the risk for Legionella. And that's a significant concern. So managing the solids within cooling tower systems is essential for Legionella control and biological management. Wave will do an excellent job on top of that, or instead of that, for managing biological control. What it will not do is treat the solids that have been settled in low flow areas of a system without recirculation. So those solids that have settled out and not been resuspended, for example, can serve as breeding grounds for bacteria. So the short answer is that both of these systems, when combined together, provide the ultimate in terms of water savings, which is why when we sell IntegraClean 2.0, which is the whole package you see here, we will guarantee water savings. If the water savings element and the corresponding cost savings are less relevant to the customer or not important, then they don't need to have the filter. But the filter is important so that we can ensure that we can cycle the water as high as possible. So customer could buy Wave only or the entire package, but the entire package supports water savings. The first part of that question around required flow rates, as long as this Wave is installed in a way that captures at least 25% of the recirculating water, we will have sufficient treatment within the system. One exception to that is if the system is on downtime, then we will mandate, as do good quality chemical service partners, that the system be flipped on 1 hour per day, simply to circulate the water and ensure flow through the system. We have a table that calculates required flows through the reaction chamber itself, and most often those flows, obviously they depend on pipe size, but we are typically looking to stay within 12 or 13 feet per second. And in most cooling tower applications, we're well within that range. Evaporative condensers, of course, run a little faster. They run a little higher. And so if flows exceed that slightly, we're not terribly worried because the turnover rate in those systems is very high. So I would say that the treatment rate within the Wave itself is well within the parameters of most operating conditions of the flow ranges of cooling towers.
Thank you. Can the system be used for boiler systems?
It's a good question. You know, Wave used to be used, the predecessor to Wave used to be used in boiler systems. There's a bit of a conundrum with that, though, because most boiler systems will use softeners to remove the calcium carbonate. When you remove the calcium carbonate, you pull out the majority of the elements or minerals in the water that one would be precipitating. So it's not really advised, and it's fairly redundant in cases like that. If a softener wasn't in place, then this will have a beneficial effect, but the payback there may not actually be there. And so it's something that we would explore, but currently our focus is on evaporative applications, recirculating evaporative applications.
Okay. I have just one thing. If anyone would like a certificate for their attendance at this webinar, send me a request and give me the proper name you'd like on the certificate to CAT, C-A-T, at griswoldwatersystems.com.
Great. Well, thank you all. I appreciate the excellent questions. I appreciate your attention. We will again aim to make a recording of this available to you. If you have any follow-up questions for Kat or myself, please don't hesitate. Have a great rest of your day, everyone. Thank you. Goodbye.